Recall that during our last class video, we worked through several applications of the Klein 8 group V8. But before we go more deeply into the group V8 and on from there to the Klein 16 group V16, I would like to explain that because much of what I have presented in these class videos is original work, choices had to be made regarding vocabulary, terminology, and notation for new ideas. Consequently, I feel mathematically compelled to share the following observations, some of which involve vocabulary and terms from the study of statistical mechanics. So what we're going to do is we're going to explore how I have been using the vocabulary that I've created and how it can be translated into the vocabulary of statistical mechanics, more specifically into the notions of macrostate and microstate. Okay? So as stated here, CMA sequences, as used above, should perhaps be called something like CMA sequence configurations. Why is that? Because each CMA sequence, as I have been using the term, is really a sequence configuration or a sequence form, where each of these sequence configurations or sequence forms have more than one particular expression or incident or manifestation or specific outcome. For example, we have been saying that there are two CMA sequences of order 4, having CMA structure type SOO, namely the following. But since we are assuming the two zeros are in fact distinguishable and that the two ones are distinguishable, the actual number of CMA sequences, and that's in quotes, for a specific CMA structure of order 4 is 8, not 2. This is because there are two CMA configurations of order 4, namely 1001 and 0110, each yielding 4 distinct CMA sequences. To see this, simply add subscripts to the two zeros and to the two ones, and you will get this list of specific CMA sequences. In general, if there are M zeros and M ones in a particular CMA configuration, then the total number of CMA sequences having that configuration is M factorial squared times the number of CMA configurations. Moreover, none of these specific CMA sequences above, namely these 8 right here, is actually fixed by any non-identity group element. The only things that are fixed or inverted are the CMA configurations, such as 1001 or 0110, or the CMA structure types themselves, namely SOO as a structure type. In the language of statistical mechanics, we can say the universal set is as follows: 0 sub 1, 0 sub 2, 1 sub 1, and 1 sub 2. Of course, the total number of permutations of these 4 distinct objects is 4 factorial, which is equal to 24. Now, if you think about the CMA structure types, they are actually macrostates in the language of statistical mechanics. There's 3 of them: SOO, OSO, and OOS. And for each of these three macrostates, we have 8 microstates. For example, the following are the microstates for the macrostate SOO. These are the same 8 CMA sequences listed on the previous page. Notwithstanding all of the above qualifying observations, I will continue to use the more parsimonious terminology that I have used from the beginning of my introduction of CMA structures and CMA sequences. The principal issue for the reader to understand is that when I use the term CMA sequence in general, I am actually referring to an entire class of individual sequences having a specific CMA structure. With that said, now let's return to the Klein 8 group that we began to talk about in depth last class period. Now, this is the diagram on the left that we had up on the screen. We did not talk about the bottom half of this diagram. That has a Cayley graph. So here is a short list of uses and applications of Cayley graphs. Cayley graphs provide graphic representations for abstract groups. Cayley graphs are a bridge between groups and surfaces. Cayley graphs give rise to examples for various extremal graph problems and are good models for interconnection networks. The well-studied circulent graphs, loop networks, are precisely the Cayley graphs of the cyclic groups. Hypercube graphs are Cayley graphs of elementary abelian 2 groups, or more generally, Hamming graphs are Cayley graphs of elementary abelian groups. Cayley graphs have been used for the construction of Ramajan graphs and expanders. Cayley graphs have been used to construct combinatorial structures, communication networks, difference sets in design theory. Cayley graphs have also been used to analyze algorithms for computing with groups, as well as provide convenient metric diagrams for words in the corresponding groups. And finally, Cayley maps are Cayley graphs embedded into certain surfaces and provide representations of groups and group actions on surfaces. Cayley graphs form a proper subclass of the vertex transitive graphs. As mentioned way back in class video 1, any cycle that is closed path on this cube that begins and ends at the same vertex results in a product of group elements that yield the identity permutation. In other words, if we start with a random packet of 8 cards, it will be returned to its starting configuration if a sequence of shuffles is performed that corresponds to traveling along a closed path on the cube that starts and stops at the same vertex. For example, traveling along the following closed path on the cube in either a clockwise or counterclockwise direction returns any packet of 8 cards to its original order, regardless of your starting position on the graph. For instance, if we begin at the vertex 1, 6 and travel counterclockwise around this closed path, this packet right here will be returned to its original starting order. Now we will go ahead and illustrate that, and I think it might be most helpful to illustrate it with an ordered packet, even though you can use any random collection of 8 cards will work just fine. So I'm starting with Ace of Hearts through the 8 of Hearts. So what we're going to do is we're going to verify this property of Cayley graphs, that if we actually complete a full cycle somewhere along the Cayley graph, here it's along that cube, and return to where we began, we will return this packet to its original order, okay? So I just kind of arbitrarily chose a place to start. So let's start down here in the bottom left. And at this point, we need not actually worry about what these labels are. The particular labels here will not affect actually the success of our journey. So we start here. The arrows will be the important thing to keep track of. So here we're going to start here. So this is where we're starting. And then if we follow the arrow to the right, we would perform a reversal of the packet. Now, as we've used before, it's a powerful alternative to use the first shall be last and the last shall be first technique. So if you remember, this is where you allow the spectator to tell you when to stop dealing. So maybe they'll say stop, and then you start dealing into a new pile. Maybe they say stop, and then you deal into a new pile. And maybe they, now say stop. We've placed all the cards down, and then you stack them. So, well, think about the name that we're using. We call it the first shall be last and the last shall be first. Well, these were the last cards. In fact, this was the very, very last card to be dealt. So what we would do is we would go from the last to the first now. Okay? And if you remember, that's actually, we can actually peek and see that this is true. That's actually equivalent to a reversal of the cards. Okay? Now, not too many people watching those actions would actually believe or suspect that that is actually just a packet reversal, especially since they're given the choice as to how many cards are dealt into each of those piles. But indeed, as you can see, it's simply a packet reversal. Okay, well, that takes us here. Now we need to go up this edge, and we'll have to, and to do that, we'll perform a 50% cutting of the cards, or better, let's perform a Charlier-1. And if you recall, a Charlier-1 shuffle is in fact equivalent to a 50% cutting of the cards, and it's just far more interesting, engaging, and convincing. So this is where you push over the top, and you're pushing over one at a time. So bottom to top, top to bottom, bottom to top, top to bottom, bottom to top, top to bottom, bottom to top, okay? So that actually is equivalent to just cutting the cards in half. As hard as it is to believe, that is actually the case. Now we are here. So to go along this edge, we have to perform a pairwise transpose. So if you remember, you do 1, 2, 1, 2, 1, 2, and finally 1, 2. And then with the pairwise transpose, for it to be a genuine pairwise transpose, we actually have to stack from left to right, okay? Just like we would read a book. That's how I normally explain it for the pairwise transpose. We stack from left to right. Now, it is true that's the opposite order to that of the first shall be last and the last shall be first, but that's implicit in the name of that shuffle, that you would actually go in the opposite order to what we've just done here. So with the pairwise transpose, we always stack from left to right, just like you read a book. Now that takes us here, and so let's go ahead and do a first shall be last, or you can just do a direct, reversal if you like. So maybe, all of these stopping points were dictated by the spectator, and then True to the name of the shuffle, the last shall be first. And so now we stack them in the opposite order to which they were dealt out. Okay, whoops, excuse me, I'm up, still dropping things. It's a brand new deck here, very slippery. So we're up here, and now we need to go down. Okay, so we'll just do a Charlier 1. There we go. We're almost home. Well, at least we hope we're home. We're way down here, and now we have to do a transpose. 1, 2, 1, 2, 1, 2, 1, 2. And then we stack from left to right, just like we read a book. Okay, so if all has gone well with our journey around this closed path, we should be back to the original ordering of the cards. And as you can see, we are indeed back to the original ordering. Okay, so that will work for any closed path that you choose to travel, as long as you finish where you started. And it won't matter if you go clockwise or counterclockwise. You will always return to, it will always be identical to the identity. That's another way to think about it. So here's a question. So why? Why should this closed path, this particular one right here, yield the identity? So to kind of think about it. Why should it be the case that as we travel along here, that all of those actions together are identical to the identity permutation? So why would that be the case? Well, if we begin at 1, 6, so maybe, I don't know, if maybe I'll put it down here for just a second. So if we begin here and eventually end here, think about it. We will have to transverse an even number of edges in each of the R, C, and T directions. Since R, C, and T each have order 2 as permutations, the total journey, as measured by a product of permutations, would produce the identity permutation. Earlier in these class videos, we did have the viewer calculate or derive some of these CMA sequences of order 8. And so let's go ahead and talk about this chart a little bit to get a better feel for the group V8. Okay, we will consider the following set of 12 CMA sequences of order 4, consisting of 4 zeros and 4 ones. There is actually one more pair of CMA sequences of order 8, but it will not be shared here. Though I do encourage the reader or the viewer to try to identify what are the remaining 2 CMA sequences. So here we have the CMA structures along the top, CMA sequences corresponding to those structure types. And then, of course, here we have the pairwise transpose, the 50% cut, and the packet reversal. Okay, so maybe just for a moment, why don't we focus on this one right here, the SOO structure that corresponds to 1, 0, 1, 0, 1, 0, 1, 0. So it really just alternating ones and zeros. So what I would like to do here is just step through some of the mathematical derivations that support the results in this table. We're going to focus our attention right now on this CMA sequence. So what is this? 1, 0, 1, 0. And then we put a little vertical bar, just aids us in seeing where the center is. It helps us to identify symmetry and other features that might be of importance to us. Down here, we have the pairwise transpose. Now, I do want to point out something that's really important, and it streamlines all that would be needed to be able to generate this chart in a matter of minutes. okay? So, for example, with the pairwise transpose, if you understand what the pairwise transpose is actually doing to a sequence, you can very quickly go from a CMA sequence, such as this one, and be able to immediately write down what the outcome would be if that CMA sequence above is acted upon by the pairwise transpose. Okay, so let me just show that really quickly here. So for instance, if you understand what's happening with the pairwise transpose, okay, so essentially I'm going to show you a fast way to fill in this whole table. You could fill in this whole table in a matter of minutes. And then I'll show you the mathematically rigorous and detailed way of justifying what I'm showing you here, actually. Okay, well, if you understand that the pairwise transpose, what it does is it takes sequences starting at the beginning and pairs, and then it just switches those entries. So the 1 goes here and the 0 goes there and so forth, right? You're just switching those. Well, what do you get when you switch those? Won't you just get 0, 1, 0, 1 repeating, right? You'll just get 0, 1, 0, 1, and our vertical bar. And there you go. We have just confirmed that, in fact, the pairwise transpose, when acting upon this CMA sequence, will give you this CMA sequence here. Okay, so there's a bit hiding. So that takes care of the streamlined way to calculate and figure these out. But there's quite a bit hiding in the phrase when I say the pairwise transpose acts on a CMA sequence. What does that really mean? Okay, so this is where it takes us into the more rigorous side of mathematical thought, because we're going to be looking at group action, okay, which can be a very difficult idea for students to study for the first time. Okay, well, let's just remind you of what a group action is. And we may not review everything that we've talked about earlier in the course, but so what happens is you have to have, you have to have a group. So you have to have some kind of group to begin with. And so just to remind you of that, this will be a set with a binary operation on it. It has an identity element. It has inverses, and the operation within the binary operation itself is associative. If you have all of those conditions being met, you have a group. Also, you need just a set of objects, okay? And there's no structure on these necessarily, just a set of objects of some sort. There's no group structure on those, okay? And so a group action is defined as follows. Phi defines a group action if it's the case that phi having domain x cross g takes you into x. Now this will be a group action on the right, by the way. We have group actions on the left, and we also have group actions on the right. This is on the right. The group's on the right. Think of it that way. Okay, so what do we mean by this, or how do we assign pairs? You can think of this as like a Cartesian. Well, it really is Cartesian product here. So ordered pairs over here. How do we assign ordered pairs to a single object in the set X. The way that we're going to do it is our set X will consist of functions, okay? So this will be a set of functions here. And so what we will be able to do, so what we have to be able to do is we have to be able to say, let me just use these names and I'll explain what they refer to. Okay, so F here, F is an element of our set X. Now, as we'll see, we will be looking at a set of sequences, in fact, CMA sequences. Well, you may recall that sequences are really just functions. They are functions. Every sequence is just a function. And this other element in this order pair is going to come from our group G. Now, our group G in the second is going to be the Klein 8 group, V8. So that's where we'll be drawing from. And the group action that we will use is actually function composition, okay? So it's important here. So our set will be a set of functions. Set X will be a set of functions. Our group consists of permutations, which are bijections. These are functions as well. So the assignment will be this pair will be assigned to F composed with sigma. Okay. Now you have to realize that, or have to check, okay, is this actually in there? Is it the case that if we have a function and we compose it with this permutation, it will be important that it gives us another function of the kind that X contains? Okay, so we'll go ahead and kind of fill in the details now with the particulars of what we're doing, and we'll see that we can meet all of the criteria here for a group action. Okay, so maybe I'll just write down here. So our set X, it will be the set of all CMA sequences of order 8, of order or length 8. Okay, so we can go off here on the left. So here are some of them. Here's 12 of them, and there's 2 more actually, as I mentioned. Technically, there's 14 CMA sequences of order 8. So that's the set of objects we have in mind. Okay. Now we're going to remind you of how these sequences are functions themselves in just a minute. But so just realize this is the set of CMA sequences of order 8, and each of those is actually a function. And then, of course, our group G is going to be the Klein 8 group, okay? And that's a group generated by our 3 shuffle permutations: a pairwise transpose, a 50% cut, and a packet reversal. Probably at this point, we need to unpack this again. If you remember, this is a compression of a fair amount of information. So here we have a CMA sequence. There's one of them. We're claiming that it's actually a function. And it's a function whose domain and range is such that when we compose it with this permutation, that's a member of V8, everything that we want to be true will be true. Namely, this composition will fall back in here of the set of CMA sequences. And then function composition actually will satisfy the requirements for a group action. If you remember, there is a, quote, identity requirement, and there's also a compatibility requirement, which is essentially an associativity requirement. Well, let's look at we're still looking at the more rigorous details of what we were able to figure out pretty quickly if we just know what the pairwise transpose is doing, boy, we can get these answers quickly, but to write it out in full detail is quite a big job. And so to be able to really even make sense of this right here, we're going to have to express our sequence as a function. And so we need to make clear that that is indeed a function. Okay, so you may recall, number one, there's a few layers of the onion to take off here, but it's important to do this at least once to feel like our table on the left over here can be deciphered by the viewer. Okay, so this is a CMA sequence, and the structure type is a SOO structure type. So we can just, an abbreviated way, a shorter way of saying that is just to say that this is an SOO sequence. Okay, well, technically, we write sequences with commas. We offset the entries. Sorry about that funny one there. We offset the entries by commas. Okay, that's normally how we write sequences. Now, if you remember, we went from here to there. And our reasoning was, well, we're only looking at values of 0 and 1. So there's no danger in dropping the commas, just pulling those out and compressing this down to that. In fact, if you like to, you can even get rid of the vertical bar, and then it'll be as short as it can be. Okay, but technically, that's how we got this. It came from this sequence. Well, now we have a bona fide sequence. Well, how is this sequence a function? I mean, how does that work? Well, a sequence is an ordered list. Well, for it to be ordered, you must be associating it with an ordered set. And the ordered set that we're associating it with is the natural numbers. And in particular, the numbers 1 through 8. Okay? So we can actually say that this sequence is defined to be our function f. And what's our function f? Well, it has as domain what we've called before n sub 8. That's just the natural numbers 1, 2, 3, up to 8. Okay. What's the codomain here? Well, the sequence entries themselves are zeros or ones. So there you go. That is a function representation of that sequence, but it's pretty important to know that we really haven't said anything except what the domain and codomain is. To fully describe a function, you have to say what it does to each of its inputs. Well, let's do that. So what does f of 1 give us? So the function f sends 1 to, so you just think, so now the input here, 1, 2, 3, up to 8, is referring to the positions, 1, 2, 3, 4, 5, up to 8. So in position 1, what is the entry? It's a 1. In position 2, what is the entry? It's a 0. Position 3, it's a 1. Position 4, it's a 0. Position 5 is a 1. Position 6 is a 0. Position 7 is a 1. Position 8 is a 0. Okay, so that is a full, faithful description of this sequence as a function. We've identified the domain, the codomain, and its definition for each element in its domain. So indeed, this CMA sequence can be viewed as a function. Well, how do we have our shuffle, namely our pairwise transpose, act on this function? Okay, well, we'll have to recall what the pairwise transpose does. So it's over here on our chart. So let me just write down here. I guess we could probably write it, well, maybe I'll just do colon. I'm kind of reluctant to do an equal sign there, but so here's a description of the pairwise transpose. 1, 2, and there's just 3, 4, and so forth, right? 7, 8. Well, if you remember, this is cycle notation for what? It's cycle notation for two-line notation. Well, or for the permutation, but there are kind of two ways that we have been representing permutations. One uses Cauchy's two-line notation, which in some ways is the fuller notation that is at least showing you the domain and codomain. It's showing you how the assignments are made. And some people would see this as a more complete description of what's going on. So what's happening here is if we were to actually have a sequence 1 through 8 or cards, A through 8 or something, and perform a pairwise transpose on those cards, this is the new order you would get. You would get a 2, 1, 4, 3, 6, 5, 8, 7. That's what you would get if you physically carried out the pairwise transpose. And that's what's happening here. 1 goes to 2, 1 goes to 2, 2 goes to 1, 2 goes to 1, 3 to 4, 4 to 3, and so forth. Okay, well, what that might allow us to do that could be helpful for some people is to just write out, now, what does it do to each one of its inputs, right? And I should also point out one other thing that I kind of glossed over. So this is 2, 1, 4, 3. Now this 2, and then this is 5, 6, 7, 8. And this will be 6, 5, 8, 7. Okay, and then I should point out over here, or maybe I'll do it at the bottom. Looks like there's room. Keep in mind, the pairwise transpose is a permutation. A permutation is a bijection from some set to itself. Always, always. That's what a permutation is. It's a bijection from a set to itself. Well, what is the set that we're using here? Well, it's N8, right? Because that's what we're doing. We are just reordering the numbers 1 through 8. And here's the new order: 2, 1, 4, 3, 6, 5, 8, 7. Okay. So T is actually it's a bijection. So, it's a function. It's a 1-to-1 onto function. Okay. Well, now we're getting closer to being able to make sense of what we talked about with this function composition. Because now we're going to compose, we're going to take our CMA sequence right here and compose it with the pairwise transpose permutation. Okay. Well, when we do that, what do we get out? Okay, so we're probably going to run out of room here, so maybe I'll just move this if that's okay. So what we're trying to describe here is, what do we get when we use the group element T from our group V8 and have it act on this CMA sequence? Well, our group action is defined in this way, namely function composition. So we can say that this is what will happen. So T acts on can be described as follows. So what's happening here is that what we called our function f, and then our group element t, which is coming, so t is coming from our group V8. That is being assigned to f composed with t. Okay? So that's really what we need to figure out to see the result of the action of the group element T on our CMA sequence. Okay? Well, to find this, we have, well, first off, it will be important to figure out if it even makes sense. Does this even make sense? Okay? Well, it does, of course, because what we will need is look at the function t, the permutation, but it's a bijection. It goes from n8 to n8. Okay? So it takes something in n8, so it takes a number, some number between 1 and 8, and gives you a number back somewhere between a 1 and 8. What is the domain of the function f? The domain of the function f is also n sub 8. Okay, so it does make sense to compose these functions. So we're going to start at n8, we'll end up in n8, and then that will feed into our function f that has domain n8. And then at that point, we will get an output of a 0 or a 1. Okay? So indeed, this will be a function from n8 to the set with 0 and 1 in it. Okay? So that's just kind of verifying that the composition even makes sense in the first place. And now let's go ahead and see what happens. So to be able to know the effect of this composition on each one of its inputs, so this is what we need to evaluate. Sorry about the O's not being all that perfect there. What is t of 1? T of 1 is 2. This is f of 2. What is t of 2? It's 1. What is t of 3? It's 4. What is t of 4? It's 3. What's f of 2? 0. What's f of 1? 1. What's f of 4? 0. What's f of 3? 1. F of 7? 1. All of that work technically was needed to confirm that result right there. To go through all those same sorts of steps for all of these would take a very long time, okay? But any one of these can be verified by going through all of the details in a similar fashion to what we've done here. And as I mentioned, once you understand what these shuffles are doing, you can kind of quickly come up with the result without ever having to write out much in terms of notation. Okay, and then down here, I just want to point out that we have the orbits and stabilizers for these CMA sequences. And this one here, I suppose we could maybe focus on this one just for a second. It says the orbit of each of the CMA sequences in a particular column, and then it gives the answer. So for example, up here, we have a CMA structure type of SOO. Here are the two sequences. The top one is the one that we've been working with. If we apply all of the group elements, and we can just focus on the generators, that will be sufficient actually. Apply the generators on these two sequences, what kinds of things do we get out? So if we have the generators in the group V8 act on each of these, what's the set of possible CMA sequences we get out? Well, what we found here with the pairwise transpose is if we act upon the top one with the pairwise transpose, we get the inversion of that sequence. Well, it's probably not too surprising to think that if we acted on the inversion of this sequence by way of the pairwise transpose, we would get its inversion, which is the top sequence that we've been working with. Okay, and you can see that in the chart here. It ends up that the 50% cut leaves this one fixed. Not too difficult to see if you just think about what the cut's doing. It's taking the top half and moving it to the bottom. Well, it's not going to change this sequence type at all. Same thing with this inversion, right? Packet reversal. Well, that will invert things again, right? It'll take this one. If you reverse the order of those values, you'll get the inversion of that sequence, which is what we've listed here. And the same thing here. If you start with the inversion of this one, and then take the packet reversal of it, you'll get the original sequence above. Okay, so what that shows then is the orbit of each of these individually, the orbit of this one right here, is the set of the two of them. It's that one and that one together constitute the orbit of that CMA sequence. Also, the two of these together in a set constitute the orbit of this CMA sequence down below. So that's why it says the orbit of each CMA sequence will be the set of two SOO sequences, which are these two here. Okay, so and a similar thing can be shown for the orbits for the others over here. The stabilizer is different, of course. The stabilizer is a subgroup of our group that holds that individual CMA sequence fixed. We can probably spot those just from the chart here. Okay, so focus on the top. Focus on this CMA sequence that we've been looking at today. Which of the generators in V8 hold that fixed? Well, does the transpose hold it fixed? No. Does the 50% cut hold it fixed? Yes. So the 50% cut will certainly be in the stabilizer of that CMA sequence. Of course, you may notice the identity permutation is always in the stabilizer because it leaves everything alone. And then there's more, right? Not just C. Now, it is true that the pairwise transpose by itself is not in the stabilizer. The reversal permutation is not by itself in the stabilizer. But if you form the composition of those two, if you take the pairwise transpose followed by a packet reversal, then guess what? It holds this top CMA sequence fixed. So that's why it's there. Now, I do want to point out that I've written RT, but our group is abelian, so I could have written it TR. It represents the same thing. I just happened to have written it RT. And finally, there's just one more element in the stabilizer subgroup of 1, 0, 1, 0, 1, 0, 1, 0. Namely, think about it. If C holds that CMA sequence fixed, and RT holds that same CMA sequence fixed, then the composition of those two, or you can think of it as the product, if you like, the permutation product of those two, will hold that CMA sequence fixed. And once again, it doesn't matter in what order you list these factors here, these group elements. Okay, and that gives you the full stabilizer subgroup for the CMA sequence listed right there. And that same subgroup here will be the stabilizer subgroup for the inversion of this top CMA sequence. Now, before we finish, it's important to talk about what will be the central focus of our next class video. We will be answering a very important question. What is actually gained by adopting a group theoretic point of view in the case of CMA structures and CMA sequences? Okay, because it's required quite a bit of work to bring in group theory, which is fairly sophisticated mathematical machinery. What is that bringing to the table that we didn't have before in our study of CMA structures and CMA sequences? That's what we'll be addressing in our next class video. So I certainly hope that you'll join me there.